Hello, 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 ladies and gentlemen, and welcome back. We're looking at more of our 2019 Euclid paper, and we are up to question number 9. Okay, so what have we got here? Looks like 4 different parts, all of them, of course, written this late in the contest. But what have we got? For positive integers a and b, we've got a function f of ab is a over b plus b over a plus 1 over ab. And as a quick example, f of 1, 2 is 3. Okay. So a part is going to ease us into this. Looks like we just need to figure out what f of 2, 5 is. And then along with f of 1, 2, we'll have a couple examples of what this function looks like. So, it's probably worth 1, maybe 2 marks, just sort of easy into the ideas being presented. So we want f of 2, 5. And so that'll be what, 5 over 2, or was it 2 over 5? It doesn't really matter. And 1 over 2 times 5, so we'll get 5 over 2, 2 over 5. I suppose we could put everything over 10. 25 over 10, 4 over 10, and 1 over 10. So that'll be 25 plus 4 plus 1 all over 10. That's going to be 30 over 10. So we get 3. And 1, 2 was 3. All right, B part. Determine all positive integers a for which f of a is an integer. Okay. I think, because it looks like we're just going to keep using this function, I think it might be nicer, especially if I'm going to plug things in, to maybe express it not in terms of a bunch of fractions. It looks like we can put everything over AB. And that might be a nicer way to write it, because if I can combine it, we'll get a single fraction to work with. And we could have gotten this 3 up here perhaps a little faster. Now, for B part, they're asking about f of AA. And we need it to be an integer, so we'll get a squared plus 1 all over a times a, which is a squared, so we'll get 2a squared plus 1 all over a squared, which I guess we could break up into 2a squared over a squared plus 1 over a squared, and that's going to be 2 plus 1 over a squared. And for this to be an integer, we want positive a. So to be an integer, we need 1 over a squared to be an integer. So a squared has to divide 1. There's only one positive integer a that will do that. So I'll write down both a being 1 and negative 1, and then I'll cross it out. So the only positive a with f at a being an integer is a equals 1, and we'll get 2 plus 1 over 1 squared, so we'll also get 3. Can this thing be, surely this should be something other than 3. I mean, if you make a ridiculously big and b ridiculously small, although maybe that's not necessarily an integer. Well, maybe that's what we'll have to do. I see the word 3 down here, or the number 3. C part, if a and b are positive integers and f of ab is an integer, prove that f of ab must be a multiple of 3. Okay. So we know f of ab is what? A squared plus b squared plus 1 all over ab. So in order to be an integer, we must have ab divide a squared plus b squared plus 1. That's literally how you're going to get it to be an integer. Now, we also need it to be a multiple of 3. So maybe, no, I don't think this may be the right way to say it. So if this is some integer k, and a squared plus b squared plus 1 equals kab, and what we need to do is show that k needs to be a multiple of 3. How are we going to do that? So if k is a multiple of 3, that means that a squared plus b squared plus 1 must be a multiple of 3. But just because you get a multiple of 3 over here doesn't mean maybe a is a multiple of 3 or b is a multiple of 3, and then that would absorb it. So I think we should look at this with modular arithmetic. There's only going to be so many possibilities. Look at a and b modulo 3. Okay, so if a is congruent to 0, so if a is a multiple of 3 is what we're saying here. And we do need to say it carefully because this is question 9, this is a written question. Let's make a nice little sort of chart. So we'll say b is congruent to 0, 1, or 2. A squared is congruent to 0. Actually, could we maybe, I think we could maybe just instead make a chart, big chart on the next page. So let us make a chart of possibilities. At least we'll be able to see when a squared plus b squared plus 1 is a multiple of 3 and ab isn't. And then in the other cases, maybe we'll have to work modulo 9 or something. We'll have a, b, we'll need a squared, we'll need b squared, we'll need a squared plus b squared plus 1, and we'll need ab. So a could be 0, a could be 1, or a could be congruent to 2. It could leave a remainder of 2 when we divide by 3. And similarly, b can be 0s and 1s. Now, the nice thing here is 2 squared is the same as 4, but 4 leaves a remainder of 1, so 2 squared is 1. So when you square modulo 3, you either get 0 if you started with a multiple of 3, or 1. So we'll get 1 here. We'll get 2, 2, 2, 0, 0. 2 here. 0 and 0 as well. So it looks like we get 2s almost every one, only when a and b are both multiples of 3. Now ab would be a multiple of 3. Now how can a multiple of 3, how can a multiple of 3 be a factor of something that quite clearly isn't a multiple of 3? That would be a bit of an issue, wouldn't it? You'll get 0s here just coming from the a, 0 from the b, 0 from the b, 2 times 2, 1, 2, 1 and 2 for our possibilities. So here's what I would do. I would highlight these ones. And I would make the following comment. If 3 divides AB, and FAB is an integer, then 3 must divide a squared plus b squared plus 1. which isn't the case for these. So that gives me my what I've got here in red. Now, as for these other cases in blue, a squared plus b squared plus 1 is a multiple of 3, but ab is not a multiple of 3. So in these cases, 3 divides a squared plus b squared plus 1, but 3 doesn't divide ab. So if, and we are told that FAB, so if FAB is an integer, then 3 divides FAB. Right? Because it divides the numerator, but we don't lose any factors of 3 when we divide out the denominator, so we are left with a factor of 3. Another way we could say that, as I already sort of had written, f has to divide a squared plus b, or sorry, not f, 3 has to divide a squared plus b squared plus 1, but 3 doesn't divide a, 3 doesn't divide b in these blue cases. So therefore 3 would divide FAB, assuming it's an integer. And of course in the red cases we've shown that FAB can't be an integer because 3 divides AB, but then 3 would have to divide a squared plus b squared plus 1 in order to not be left with an over 3, or a 3 in the denominator. So I would say that's, yeah, I'd say that's clear for C. Working modulo 3. All right, and based on our evidence, the 3, you got a 3 here, and I think we did comment F11 should also be a 3. Is there a way to show it's got to be exactly 3, but maybe that's too hard and they had to do multiple of 3? Or maybe that's what we're going to have to do in D. Determine 4 pairs of positive integers a, b with 2 less than a less than b for which FAB is an integer. Okay, we know FAB would have to be a multiple of 3 from C. We already have seen F11 is 3. That came from B. F12 was 3. This was given. And F25 is 3 from A. Okay, so I don't see any reason why those numbers in particular are giving me 3. We could try experimenting with other things, but we need our smallest number to be bigger than 2 now. So we could try maybe a 3. Anything work with a 3, for example? Except, well, didn't we see, yeah, over here, this chart should be able to help us narrow down our options. Can't use any multiples of 3. So I can't have 3 as my smallest, maybe 4. Maybe there's a way to work this with 4 and with 5, but I don't know what FAB is supposed to be. I know it's a multiple of 3. I've already stated my suspicion that maybe it's always exactly 3. How to prove that is beyond me, because if you make A really, really big, A over B can be as big as you like. But maybe then you lose the integer part of all this. But we just need to determine 4 pairs of positive integers. We don't. They're not asking for how many pairs. They're not asking for all pairs. They're not asking us to explain why 1, 2 is an answer. We just need sufficiently big examples. So we could just say, I don't care about the other possibilities. I've seen so far that it's equal to that a lot of these answers are equal to 3. Maybe try something like F4B is equal to 3. Try and solve that. Okay. I'm going to just explain. I've seen it equal to 3 so many times. I'm just going to try FA equal to B. Okay. A can't be 3 because neither A nor B can be a multiple of 3 from our little chart in C. So let's try 4b. So that would be 3 is equal to 16 plus b squared. So if I assume a and that the answer is 3, I should be able to get a nice little quadratic here. So 12b is 17 plus b squared. We're not going to get integers from this. There's no multiples of 17 and no possibilities. Well, we could try f at 5. I mean, 5 worked here. We should get a quadratic, and 2 should be one answer. So try 5b. So 325b squared plus 1 over 5b. So we get 15b. So I guess we could say b squared minus 15b plus 26 needs to be equal to 0. And I know I can do 2 there, and 13 would have to be the other one. So 513 is 3. Oh, now that's kind of cool. And so now I know 13 should work, and 5 is a solution. So can I show that this will always work? So I'm going to try and prove that, because then there's at least some justification for what I'm about to do. So suppose FAB equals 3. A less than B. I claim there is a C with B greater than C. So FBC is also equal to 3. You have this nice little chain here. Okay, so here's my reasoning. So the whole thing is symmetric, so it doesn't really matter where we place B. Okay, so if B gives a solution, there should be 2, one lower and one above. That's sort of what I'm claiming. Okay, so 3 being equal to x squared plus b squared plus 1 all over bx rearranges to b squared minus 3xb plus x squared plus 1 equals 0. And then if a is an integer, solution, then what have we got? B squared minus 3xb plus x squared plus 1 equals 0. We should be able to factor this. So one factor we know is A, the other factor we know is C. But then 3x is A plus C. A is an integer, therefore C is 3x minus A. Is an integer, is that? No, I guess what I need is put A here and A here. Right? Or, hold on, what are we doing here? So it's the 5 that gave me the minus 15. So that's my known solution. So I should treat this more like, so x should have been actually my variable for my quadratic all along. A is a solution, so we get 3bx and we get x minus a, x minus c. And so my solution, my new solution C should be 3b minus a. Right, that should work. And so what we've seen, for example, 2 and 5, and then we got 13 next. And so 3 times 13 minus 5, I should get 34 next. And I'm starting to realize these look suspiciously like some Fibonacci numbers. Okay. So f of 513 is 3. But then 1334 is 3. And then 34, so 34 times 3 is 102. Minus 13, it should be, oh, look at that, 89. Another multiple. Why? Yeah. Yeah, minus 7, minus, yeah, 3. Okay, 89. And then we just need one more, so 89. 89 times 3 should be 270 minus 3, so 267. And then minus 34, 233, which is another Fibonacci numbers. Now, why these are Fibonacci numbers, and if it actually is only ever equal to 3, is something that I can work out after the contest. I can puzzle with on my own. But they wanted 4 pairs. There we go. And we gave them a nice, clear way to generate them. Okay? And this is sort of based off our observation that we get this quadratic. If you assume 3, so like maybe if we assumed 6, that this would work out. Actually, maybe that's a way to prove that it's got to be 3. Hold on for a moment. So the question's over. So, you know, blah, 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 like and subscribe, whatever you want to do. But I want to see if, can I prove that this has to be 3? Because now I'm interested. And is it just sort of a coincidence that the Fibonacci numbers show up this way because some of them satisfy this pattern? So suppose there are integers FAB that are equal to k, which is an integer here. Then b is known and a is a solution. I will say a is less than b. A is a solution to this, which will turn into sort of a quadratic. So x squared plus b squared plus 1 over bx minus k equals 0. And we'll get x squared minus bk x plus b squared plus 1 equals 0. Okay, and so this factors to x minus a. If it has another factor, it's got to be an integer. So C has got to be KB minus A. All right? So if I have one pair, I should be able to sort of work backwards. So if AB is such a pair, so it'll be A and it'll be 3A minus B. And then 3A minus B, not 3A, KA. And then KA minus B, multiply that by K, so we'll get K squared A minus KB, and subtract off A from that. So K squared minus 1A minus KB. I don't know if this is necessarily going anywhere. Though that's the problem. Is I'm trying to work backwards and say, because that 1, 1 was quite nice as an answer. I don't think we get something. I don't think there's necessarily, just because I say K is an answer doesn't then force there to have to eventually be a solution that goes one something. But that's what I'm trying to do, is I'm trying to say, okay, if you can get one pair, you can get an infinite number of pairs, and you should be able to work it backwards a bit. And then we get this one. I'll do one more, but I'm not seeing any pattern, so maybe I'll have to leave it for you guys. So multiply by k again, you'll get k cubed minus ka minus k squared b minus the other solution. We'll get k cubed minus 2ka minus k squared minus 1b. I'm definitely noticing some numbers. There's k squared minus 1. Now there's a k cubed minus 2k. There might be some sort of GCD argument here. That I can't quite think of yet. Let's see, it went 1, then k squared minus 1, then k cubed minus 2k. Multiply the last one by k and subtract the one before that, and that might be why Fibonacci is coming into it a little bit. So k to the 4 minus 2k squared minus another k squared plus 1, so minus 3k squared plus 1. So those seem to be the coefficients in front of the a's and the b's, but I'm not seeing anything there. I'm sure if we looked at it mod k, but that's a whole other story. So I'm going to leave it to you guys. Is 3 the only possibility, and is there a better way to see this Fibonacci connection? I don't know how Waterloo did their solution, so they might have a real obvious way, like why it always has to be 3, or maybe they do more than I did, which is all I did was say, hey, these kind of look like Fibonacci numbers. That didn't really help us with our solve. It was entirely showing this relationship. And the only reason we said equal to 3 is because they gave us 3 examples of equal to 3 and nothing else. Okay? But there we go. So I'll leave that for you, and I'm going to move on to question 10 now. So if you're interested in that, please feel free to join me in the next video for question number 10.